So we did a second order, we analyzed a second order system and we determined the coefficients B1 and B2, right? Now, there are more useful things that actually we can determine by looking at the transfer function. So let's say you have a transfer function of a second order system. And if you look at the denominator, of course, the second order system, you have 1 plus B1 plus 1 plus B1s plus B2s squared. But for a second order system in general, you can write the transfer second order polynomial in the following form, which is a useful form. Where omega n is a natural frequency of a second order system. Right? This basically goes back to the second order differential equation. And Q is the quality factor, which basically you can also write Q is 1 over 2 zeta. Or zeta is 1 over 2 by definition. Zeta is called the damping constant. Q is the quality factor. And quality factor, the most fundamental definition of a quality factor is basically 2 pi times the energy stored in the system divided by the energy dissipated per cycle. That's the quality factor of the system, right? Resonators have, the higher the quality factor, the more energy they store, and the less they lose every cycle. So you can write it this way. Now, but if you write it this way, then it tells you something, right? Q is also, it can be related to B1 and B2. Now, omega n is a measure of the natural frequency at which the system resonates, if you have a resonator, if you have an underdamped system. And Q is also a measure of peaking. To the first order, if you have a first order system that peaks, the peaking above the lower frequency value, this is Q. The amount of peaking is the Q. So this is a good way of anticipating how much peaking you do. And this frequency is actually a little bit off from omega n. It's actually omega n times 1 over square root of 1 minus 2 zeta squared, but it doesn't matter. So this is approximate, but for a high frequency system, this is omega, approximate, close to omega. But you can actually calculate it more accurately. It's basically, this is exactly 1 over 1 minus 1 over Q. So this is the frequency of peaking. And if Q is high, then this becomes approximately equal to omega. So this gives you a good measure of where to expect, it's actually 2Q. Where to expect the peaking and how much peaking to expect. Now, but how do you relate those to B1 and B2? Well, you can look at these and it's easy to calculate them in terms of B1 and B2. If you have a second order system, what is omega n? It's 1 over square root of B2, right? Which you can write in terms of time constants. It's 1 over square root of tau 1, 0, tau 2, 1, which is equal to tau 2, 0, tau 1, 2. And what is B1? I'm sorry, or Q. Sorry. What is Q? Q is the square root of this divided by that. So the square root of B2 over B1. Which, again, if you use this expression for the time constants, you can write it as tau 1, 0 plus tau 2, 0. And it's more accurate. It's going to look a little more regular and more symmetrical if you look at 1 over Q. 1 over Q is going to be 1 over this. So you get tau 1, 0 over square root of tau 1, 0, tau 2, 1. Right? It simply can be written as square root of tau 1, 0 over tau 2, 1. Plus, now, if I know that, so this one is going to be tau 2, 0 over square root of tau 1, 0, tau 2, 1. But now I know one thing. I can use that identity that I have. That this is tau 2, 0, tau 1, 2. So this again cancels that. So I get tau 2, 0, tau 1, 2. And typically, one of these things dominates. Right? And the one that dominates determines the Q, the quality factor. So this is a useful thing because now, using determining B1 and B2, you can not only do this, you can also determine how much peaking you CL. And you're interested in the transfer function, V in, V out, the voltage transfer function. Now, okay, so let's calculate these things. So in this case, I'm only interested in determining where it peaks and how much peaking I have. So I don't even need to worry about the numerator terms, the H's. So what do I need to determine? So I need to determine the tau pi 0. What is tau pi 0? You should be able to tell me quickly. Rm C pi, right? Because you see Rm. Looking into here, open from there. And then you can, what is tau L0? Again, Rm CL. And what is, I don't know, just like pick one. Tau L pi. Short pi, you get R1 CL. Right? So these are the time constants, that's all I need. Now, let's do it numerically. So these are basically like all I need. So if I wanted to write those terms, so let's just write the terms. So B1 is going to be Rm times C pi plus CL. So that tells me, and B2 is R1 CL. So my omega n, the natural frequency, I should expect it to be 1 over square root of, B2 is R1 CL times Rm C pi. So it's R1 Rm C pi CL. So this is the frequency at which, if it peaks around that frequency. This is a natural frequency. I mean, we can calculate the peaking more accurately with that expression, but this is a good approximation. This is natural frequency anyway. And then the cube, square root of B2 over B1. So it's square root of R1 Rm C pi CL over Rm C pi plus CL, which you can basically write as square root of R1 over Rm C pi CL 1 over C pi plus CL. Fine. So you can actually control the quality factor by changing the parameters here. You can design it to have the right Q. But I can make it numerical now. So let's assume that C pi and CL are each 50 femtofarads. And let's assume that Gm is 20 millisiemens. And R1 is 2 kilo ohms. I think those are the numbers we had in our example. Yeah. Okay? So let's see what happens. If you pick these numerical values, so what is V1? So Rm is going to be what? It's going to be 50 ohms. 50 ohms times 100 femtofarads. So it's 50 times 100 femtofarads is 5 picoseconds, right? Yes.
Is tau L0 Rm plus R1 times C?
That's what I think too.
I'm sorry, which one? Tau
L0.
L0. No, because this is open, right?
Right.
So what happens is that this is a MOSFET. You can think about reflection rule. If you reflect it, this becomes divided by infinity, so it becomes 0. Another way of thinking that this voltage and this voltage are the same, because there's no current flowing, DC. So this is the same voltage, so this is like ground. So it would be just Rm. If it were bipolar, then this would be Rm plus R1 divided by beta, or 1 plus beta. But in this case, effectively, since beta is infinity, right, so it basically gets divided by infinity, so it's not beta. Okay. So numerically, this is B1 is 5 picoseconds, and B2 is basically this part, which is 50 ohms times 50 femtofarads, so that's 200. Okay, let's do this. So this is 2.5 picoseconds, right? Times R1 is 2 kilo ohms times 50 femto, that's 100 picoseconds, right? That's 250 picoseconds squared. Those are the numbers. my Q? Quality factor. Q is square root of that divided by this. So it's square root of, so I get a picosecond out of that, out of the square root cancels this picosecond, so I'm left with unitless quantity. So it's 250 divided by 5. Square root of 250, that gives me a 5 plus square root of 10, so that's square root of 10. And that's approximately 3.16. So it gives me, it says that I have a peaking ratio of 3.6. Means that compared to the flat gain, before it starts dropping, I should have about 3.6. And in dB, is that 20 log of 3.6, that's 10 dB. It's 20 log of square root of 10, which is 10 log of 10, which is 10. So it predicts 10 dB of peaking, which is quite a bit of peaking. And the natural frequency, omega n, is going to be 1 over square root of whatever, 250 picoseconds squared, which basically is approximately around 10 gigahertz. Now, if you go and look at the SPICE simulation, if you simulate the SPICE, and you can see those results on in figure 464, you see that it's peaking. You see a few things actually there. It's peaking, and it's peaking by, when you measure it, it's peaking, SPICE shows the peaking of 10.2 dB as opposed to 10 dB. So we are close. We're 0.2 dB off. But we predicted the peaking relatively carefully, accurately. And then also the frequency of peaking is at 9.8 as opposed to 10 gigahertz. It's close. It gives you shows you a sense, it gives you a sense of how much peaking you have. Now, in general, one of the things to remember, what is the condition for a second order system like that to have complex conjugate poles? Because you know, a second order polynomial written like this can have real poles, two real poles, or a pair of complex conjugate poles, right? The roots of a quadratic equation. The condition is simple. The condition is that if Q is greater than 1/2, then you have complex conjugate poles. So anytime you have your quality factor is greater than 1/2, 0.5, you are dealing with complex conjugate poles. So you can immediately tell by looking at the value of the Q whether or not you have complex conjugate poles. If you have a Q of like 0.1, 1/2, it doesn't mean that you have peaking. It just means that you have you're starting to have complex conjugate poles. But anyway, so here's the thing, and you can use this to determine that you have whether or not you have complex conjugate. So in this case, in this numerical example, Q is 10, or I'm sorry, Q is 3, square root of 10. So it means that we have complex conjugate poles. And if you look at the Bode plot carefully, what you see is that, well, you see the peaking. And when you look at the phase gives you additional information. What does the phase plot tell you? If you look at the phase plot, what do you see? You start from 0, then you go down to like minus 160, 155 degrees. Very steep. See how steep that curve is? If it were like for regular poles, like real poles, that the slope of that curve is that it starts from a decade below to the decade above for 90 degrees of phase. So it goes through like 160 degrees of phase over no time, over like very, very short distance. It's like a tenth of a decade. So that slope tells you that you have very underdamped poles. But then it comes back up. Why does that happen? What does that mean? It means that you have 0, right? Do you have a 0 in this circuit? Well, think about it. Do we have 0? We have 1, right? When you short circuit this guy, you have a transfer function. It's at left half plane 0, so it contributes positive phase. So it brings it back up. And you can even see that in the amplitude plot if you look carefully. You see the slope is higher first, and then it comes back, it becomes shallower, a little less steep. So all of that is very consistent, right? As it should be.
talk more a little bit more about underdamped poles. What do you mean by that?
Okay, underdamped system basically. I mean underdamped. So underdamped system basically means that you have complex poles where basically the time domain response, a step response for instance, will start ringing. So an overdamped system, a step response looks like this. There's a critically damped system which basically just barely makes it there. And beyond that, if you start increasing the Q, as Q goes up, or as zeta is going down, the damping factor is going down, right? So what happens is that your system becomes more and more underdamped. In other words, you think about that, you remember where the poles were and we looked at the step response? When we were talking about the frequency. So initially, if you have a pole that's sitting there, the step response is going to be like that. Right? Now, if you have a pair, or if you have two of them, still you can get something like that. But then, what happens is that if you get a pair of complex conjugate poles like that, then the step response looks like that. And the farther out they are, the more underdamped they are. Basically, this determines the slope of this angle determines zeta, or Q. The farther out there, the larger the ratio of the complex, the imaginary part to the real part, then the more ringing you get. And higher the Q. Which just makes sense, right? For a system to ring, it has to keep a lot of energy. Because you hit it once in a step response or an impulse response, right? You hit it once, or if you have a nice glass, right? I mean, like wine glass, right? If you have a good one, just hit it, or pitchfork, right? You hit it, it just goes. But what it means is that basically it just keeps a lot of energy. It loses very small amount of energy each cycle that it can go for a long time. So this ratio is large. Has large stored energy to dissipation, energy dissipated per cycle. And that means that if you hit it once, it goes ding. It rings. If the system is dissipated, highly dissipated, what happens if you hit it once, it goes like this. Or like that. This is a highly dissipated system. But if you hit something that's, what is that thing? This is better. You have to find something that high after bringing each one.
And it's ringing at the frequency where the drop off is the most.
This frequency is the natural frequency. So yeah, it's close to that omega n. The peaking happens slightly off. So the opposite. This is times omega n. So this is a correction factor to omega n. If you want to get exactly where it peaks, this is where it peaks. If Q is large, for large Qs, this basically is omega n. You see, this is basically 1 minus 1 over 20. Then square root. Right? So it's very close to omega n. But if your Q is like small, then this correction can matter. Any other questions on this? Well, this is actually very useful in second order systems because, or higher order systems too. So you can use it as an approximation. All you need to do is determine V1 and V2 and calculate the square root of V2 over V1, and that gives you a Q. That tells you if your system is underdamped or overdamped. And a lot of times you don't need to calculate this accurately. You don't need to calculate all the terms of V1 and V2. Because when you're doing it numerically, you can tell which term is dominant. Right? You can see, okay, well, I have like 5 terms in V2, but I don't need to calculate them because 4 of them are really small compared to this one guy. So I calculate that one guy, and then the 2 guys from the V1, and then calculate that ratio. It becomes a back of the envelope calculation. You just need to be clever about it. You need to keep your eyes open. Okay. Last example of a second order system. So look at this and tell me what it does. What does that notch is closer to 1. It's a notch filter, basically. What happened? Think about it. Think about high frequency and low frequency. At high frequency, does the signal go through? Very high frequency. Yes or no? Yes. What does it go through? It goes through the capacitor. At low frequency. It goes through the inductor, right? And there's some frequency at which these two impedances can cancel, the admittances can cancel each other out, and then this can present a very large impedance. And that frequency basically can just become a band stop or notch, as you pointed out. So I expect this to do, the transfer function to do this. Something like that. Like that. Right. So, how many poles, how many zeros? Start with poles. How many poles? How many independent initial conditions can I define? 2. I can set this voltage to be 1 volt and this current to be 2 amps. Right? Right? Because the inductors for inductors you have to find currents, right? So I can define that current to be 2 amps and this voltage to be 1 volt and nothing happens. So I have 2 independent degrees of freedom. I have 2 poles. Zeros. How many zeros? At this point, 2. 1, 0. How many people say 0 poles? No zeros. 0 zeros. How many people think 1 0? Okay, let's look at it. If I short circuit this capacitor, would I get a non-zero transfer function? Yes? If I open circuit this inductor, do I get a non-zero transfer function? Do I get a non-zero transfer function? If I open circuit it, I have to give infinite value, right?
Well,
Open this, and this is not there. Does anything go through? No. 1, 0? Are you sure? What was the criterion? Exactly. The criterion is that the maximum number of elements that can be simultaneously infinite value.
you can do that.
So now can I simultaneously infinite value both of them and something goes through? Infinite value in this guy means shorting it, infinite value means opening this guy. So this goes through. So this is one example where it kind of shows you why that criterion was defined that way. They have to be simultaneously infinite value. See, when I write the H's, you can see. Let's write the H's. So what is H naught? I'll get back. What is H naught? At 0. At 0, basically, this is open, this is short.
GM.
So this is the gain of this guy, GM, whatever. R1. Well, it's GM times the total resistance you see on this one, right? Which is R1 parallel R2. Whatever that is. Right? Because the inductor is shorted, the capacitor is open. There's 0 value. 0 value inductor is short. That's why we took the pain over the last several lectures of not saying shorting and opening, saying 0 value and infinite value. Because they're mean different things for inductors and capacitors. Okay, it's H now. Fine. What is HC? Then C is infinite value. And L is 0 value. If L is 0 value, if you short this is short of 2, so both of them are short. So you get the same thing, so it's H naught. I don't want to repeat writing, there's a minus. Yeah. But, and then, what is HL? When C is 0 value, of course, because they haven't specified it, so it's short open, and L is infinite value, which means that it's open 2. So this is what? 0. So if you stop at this point and say, well, okay, well, it seems that I have only one of them makes it non-zero. So you may incorrectly arrive at the conclusion that you have 1 0. But now, what you really need to have to find is the highest order H that's non-zero. Because that would give you the highest order A in the numerator, right? Like the A, in this case, A2. So what is HLC? Meaning, both of them are infinite value. This guy's shorted, this one is open. This guy's shorted, this goes through. So it's H naught.
still be.
No, because still you satisfy the criteria of the maximum number of them that can be simultaneously infinite value. Maximum number of elements, right? So first of all, it can't be more than the number of elements, right?
Sure.
In this case, you have 2 elements. So the maximum number of elements possibly that you can be, that is 2.
So in a higher order system, nth order system,
Nth order
the
system.
highest.
The highest
n.
order H, that's non-zero, tells you what's the highest order A that's non-zero, which tells you what the order of the numerator is.
So it takes the dominance.
Exactly. Because remember, H here, A2 depends on A1, 2. Okay? So, that's fine. Okay? And now, and it's used generally, by the way, this is another hint in terms of, another kind of like point of practice, is generally if you can specify higher order H's in terms of H naught, do. As much as you can. Because remember, all of them will have, the numerator looks like some H naught plus some sum of some time constant, some HI's plus some HIJ's, etc., etc. So as much as you can define these in terms of H naught, you can factor all of those out and make it very simple. They won't clutter your numerator. If you can, this is a good habit to specify in terms of H naught, if you can. Okay, now the time constants. How many do I need to calculate, by the way, to determine the complete transfer function? How many time constants are there? Yeah, I mean, there are 4, but how many do I need? 3, right? But let's just look at it. H tau L0. Meaning the time constant, the resistance seen by L when everything else is 0. This guy's not there, this guy's not there. What's the resistance seen between these 2 points? What is it?
R1 plus R2.
R1 plus R2. Right? R1 plus R2. They're connected, these 2 are shorter through here, through ground. Tau C0. What's the resistance seen by the capacitance C when the inductance is 0 value? 0. So 0 times the capacitance is 0. This needs to be multiplied by, or it's the inductor divided by that. It's L over. Right? And then I need one more time constant. Which one would you calculate? Tell me. Tau LC or tau CL?
Tau CL.
The 2 time constants? These 2? Why should they be the same? Because the product of this and that should be the same as product of this and that. But they're not individually the same. These 2 are not the same, so this cannot be the same. Actually, that tells you something about which one will give you an interesting result and which one gives you a boring but more useful result. Which one will you calculate? Tau CL. Why? Okay, alright, exactly. So what you know already what this one is, right? You're thinking this is infinity, but we'll check that out later. Tau CL. What is the tau? What's the resistance seen by C when L is infinite valued? So this is not there. Again, R1 plus R2 C. And is this infinity really? Tau LC. That is the time constant seen by the inductor when the capacitance is infinite value, which is sure that the resistance seen is 0, but it's L over R. It's L over the resistance seen, which is infinity. Which makes sense. Now, if you run into a situation like this, how do you fix it? If, let's say you're somehow forced to use these time constants, what do you do? You put an Rx in series with one of these guys, and then set it to 0. You'll see it cancels out, and you get exactly the same result. Let's just do it. See, these guys actually can give you the correct results. I'll put it in series with L, put Rx. Okay? So, in that case, what is the time constant? What is tau C0? No, careful. Because now if it's shorter, you see Rx here, but it's in parallel with R1 and R2. So this becomes Rx parallel R1 plus R2 C. And this one tau LC. When this one is shorted, what is it? It's Rx, right? It's shorted across here, so that doesn't matter. So it's Rx, but it's basically L over Rx. Okay? So you multiply these two. So let's express this in terms of Rx. Let's call this as R. Let's call that R. Rx, Rx plus Rc. Then multiplied by that gives you L over Rx. These guys cancel, and you set Rx to 0, so this goes away, this cancels that, you get LC. Which is the same as you get from the product of these two. This gives you tau 0, tau Cl, which is LC. So it's a lot easier to do it that way, in the hard way. So, but that's easy, that makes it easy. So this is B2. B2 is LC. What is B1? The sum of these two is L over R1, so I'm done, right? It's L over R1 plus R2. I was done a long time ago, actually. But. And then, how about the numerator? So I can factor H naught out. Okay? So it leaves a 1 plus what? This one times that guy is 0, and that one times that guy.
No, times the other one.
No, I'm sorry, times that one.
Yeah.
Sure, that's fine. It's 0 still. So the first order term is 0. How about the second order term? It's this guy times this product. So H now that factored out, so I'm left with LCS squared. That's it. Right? I'm taking a lot longer than I should, basically, with these, but I want to just go over some of the intricacies of these things. When you do it yourself. All right? Any questions on this? Okay. And now, okay, what's the quality factor of this thing? How much peaking should I expect? Parametric. What was the quality factor? Square root of B2 over B1. This is something that this is a useful thing to remember actually.
B1 is
So it's square root of LC over L over R1 plus R2. So it's R1 plus R2 times square root of L over, what's that, C over L. So you can actually adjust the Q. This is useful from a design perspective, right? But if you're designing this to have some sort of a no, so this basically tells you how deep this notch is. You can control it by controlling R1 and R2 and L and C. And you can control its natural frequency. If I ask you what's the natural frequency, that's trivial, right? This should not surprise you. Which is 1 over square root of B2. This should look like a familiar result. Any questions on this? Okay. Okay, well let me do, we have like a couple more minutes. Let me do another example. This is an interesting one. A little different. There's something different about this one, which is so think about this circuit. Two NMOSes, cross-coupled, an inductor, a capacitor, and if you wanted to bias it, you can bias it from the middle of the inductor. So let's assume that's biased properly. And let's say a resistor, or let's call it a conductor, G naught, CL in. Let's call it I in and V out. That's fine. I in and V out. Let's say my input is this current and my output is this voltage. So, what's the behavior? What can you say about this transfer function? What is H naught? Or in this case, the transfer function had units of impedance, right? It's a voltage divided by current. So I can write it as Z naught, or I can write it as H, doesn't matter. So in this case, just let's write it as H. So what is H naught?
You have to calculate the resistance from.
What is the voltage across this thing at low frequency? By current. Where would all the current go through?
Induction.
Through the inductor, right? So what's the voltage?
0.
0. So H naught is 0. How about HC? That's doubly 0. How about HL? That's when the inductor becomes open, right? So then you have to know what the resistance is, and the capacitor is not there. So neither one of them are here. What is the resistance of this thing? We've done this before, right? It's a negative resistance cell because of positive feedback. Actually, it's minus 2. Then the conductance is minus 2 over GM.
Resistance.
The resistance is minus 2 over GM. Or conductance is GM over minus GM over 2. So you have these two in parallel. So the total conductance is minus GM over 2 plus G naught. So whatever that is, so you can write it as minus 2 over GM plus 2 G naught. Did they calculate that at all? Okay, fine, yeah. And then that's defined as G effective. So that's defined as G effective, or minus that. G effective, this calculation. Okay. So G effective, that's what G effective is defined as G naught minus GM over 2, which is the total conductance. This conductance minus the plus that conductance, which is negative. So this becomes minus G effective. Well, actually, no, sorry, it becomes G effective. G effective. And then, well, 1 over G effective. And HLC is what? L is open, C is short. So it's 0 again. So this is only non-zero term. Time constants. Tau C0. What is the capacitance, resistance seen by the capacitor when inductor is in the value? 0 value, yes.
0.
It would be minus 1 over G effect.
The way I defined it, actually, it's correct. But G effective can be negative. In your handout, it's defined as, so let's keep it consistent with your hand. This is correct, but let's just keep it similar to your handout. Then it becomes minus G.
No, that way the handout is wrong. Because the handout
It has to be, no.
is
No,
the
it's
same G effective
no.
and HL is 1 over G effective.
Okay,
Those
it's correct. Just give me a second. It doesn't matter. It's not a question of minus sign. We'll get back to that. Let me just fix the rest of it. And then we'll get back to that. Tau C, what is tau C0?
C0,
It's simple.
Zero.
What's the resistance seen by the capacitor when the inductor is 0 value, which is shorted? The inductor is shorted.
0.
0. What is tau L0?
G effective.
The inductance, what is the capacitor, what is the resistance seen by this one? Minus G effective, right?
L over.
And, well, L minus L times G effective. Right? And what is tau? I should probably go with the tau CL, right? Because this is a non-zero one. What is the tau CL? What is the capacitance seen by this guy when this is infinite value? This is gone.
Same. Minus.
Same thing. So now it's basically C minus C over G effective. That's an RC. So therefore, B1 is minus LG effective, and B2 is the product of these two, which gives me LC plus LC. Correct? So the transfer function looks like 1 minus LG effective S plus LC S squared, and in the numerator I have minus 1 over G effective times this, so they cancel, so I'm left with LS. Right? That's the transfer function. Right? Okay, so what do I have? G effective, if GM over 2 is greater than GO, if I have a large enough GM, then G effective becomes positive. So let's assume that I have a large enough GM, because if I don't have a large enough GM, basically my transistor is not doing anything useful. It's like not having it. So if I have a transistor that's doing something useful, then G effective is positive, this becomes negative. And then this is basically what you have. What does this look like? Okay, what kind of poles? I have complex poles, right? But are they left half plane or right half plane?
They're right half plane.
So it's a quadratic equation. This term is negative, right? So I have a pair of complex conjugate poles that are right half plane poles. So this gave me this a pair of right half plane complex conjugate poles. What does it mean? It means that if this condition holds, basically if G effective is greater than 0, it means that the step response of this thing, or impulse response of it, is a growing exponential. What have we made? An oscillator. And of course it won't grow forever, because at some point the nonlinearity will kick in and keep it constant. So it will have a constant amplitude, and this is an oscillator if that condition holds. So you can see it holds also for things that you have on the right half plane, or right half plane poles. Okay. So you can use this to analyze oscillators as well. Right? And so far we've just done a limited second order system. We go to higher order things that can explain more additional, more things. Anyway, any questions on this? Is this correct? Are you okay with this now the way?
I think there is an inconsistency because HS is similar with handout, but HL is not, because they have to.
Okay, let's talk about it offline. If there's an error, we'll let the class know at the end of the maybe next session. Okay. If there are no more questions on this, I'll see you on Friday.